So in the ammonia industry, what you find is a great deal of consolidation. You have a small number of big players that account for, basically 90% of the production. And you have very little small-scale distributed production. The vast majority of plants are over, 100 tons per day. Some of them are 500 tons per day, 1,000 tons per day. And these plants are located usually nearby uh, natural gas wells, natural gas production facilities, and the current model where we take natural gas, or for that matter, coal. We don't really do coal in the U.S. It's we in China they make ammonia from coal. But that model, based on hydrocarbons, it is not necessarily amenable to decentralization, where you produce it at the source. Um, and so what you actually find is that if you integrate small scale ammonia production with existing sources of low cost electricity, it's not really about renewable versus, CO2 generating sources, right? It doesn't really matter how you generate the energy, whether it's renewable or not. You actually find that the cheapest source of electricity today is, lo and behold, photovoltaic panels, regular solar cells. That's actually the cheapest way to make power. It's even cheaper than, fissioning uranium-235. So, which is amazing considering the energy density of nuclear is about 2,000 times more than solar. So cost doesn't necessarily follow energy density. So you have all these people out there saying, we have to so-called decarbonize, right? All of these industries. That's not really what I'm interested in doing. I mean, decarbonization is a very complicated issue, and I'll probably make a video on that sometime. But my focus really is on how to produce ammonia, um, for farmers, or for as a fuel for that matter. Really, I was first looking at it as a fuel because kind of fertilizer production is pretty boring, right? And I was looking for ways to produce ammonia for cheaper than the current, centralized production model, where increasingly they're charging almost $800 a ton. And if you imagine natural gas is rock bottom prices, less than $4 per million BTU, or 1,000 cubic foot. You'd expect ammonia to be a lot cheaper, but it isn't. So what's going on is that this consolidated industry is taking advantage of its position, and it's charging high prices because it's got the bargaining power. So the distributed production model really makes sense to break that production monopoly. The current prices of ammonia as of April 2021 was $700, $710 per ton. So the price of natural gas, on the other hand, was only $2.50 per 1,000 cubic feet, and 1,000 cubic feet is about 19 kilograms. Okay, so this translates to a price of natural gas of around 13 cents per kilogram. Now, what's interesting about that is that the price of water, consumer water, right, is typically about $1 per gallon, right? So natural gas is actually cheaper than water, or at least in April. And it's, the price of natural gas is ticked up to nearly $4 per 1,000 cubic feet. So the price of producing hydrogen from natural gas should only really be, $1 to $1.50 per kilogram, because you need a stoichiometric ratio. You need 3 kilograms of CH4 to make 1 kilogram of hydrogen. Now, it's actually not the stoichiometric ratio of H2 content by mass, because you actually get more hydrogen from the steam, the reverse water gas shift reaction, where you use the carbon monoxide to produce additional hydrogen. All right, so you need 3 kilograms of CH4 to make 1 kilo of hydrogen. So if you add up the price of natural gas, just the bare natural gas cost, right? It yields a price of ammonia of 213 per ton. Now, of course, you need 178 kilograms of hydrogen to make 1 ton, right? So you take 178 and multiply it by 1.5. Again, you're sort of in the 200 per ton range, right? Which makes sense because if you look at a very interesting chart that's going back 20 years or so for Russian ammonia prices, and in 1998, I think it was, Russian ammonia prices bottomed out at about 250, or was it about $200 per ton? So we know when natural gas is really cheap that we can make ammonia for about 200 per ton. Now, what's interesting about that, right, is that that's the totals, that's the selling price, right? That's including perhaps some transportation. That's including, obviously, the capex of the actual chemical plant. So as for capex, the capex of the most recent estimate I could find was a large ammonia plant built in China. And I'm using China as an example because if you look at, let's say, for example, we take up nuclear reactors, right? If you're if you're a nuclear evangelist, you're not going to cite the price of the AP1000 construction in Georgia, which is like over budget and way off schedule. You're going to find the most attractive price, and that's for the AP1000. The Chinese build the AP1000 for $3,000 a kilowatt, half the price of the AP1000 construction in Georgia. So it's double the price. It's the same reactor. It's the exact same reactor, right? The same power, because it's a price per kilowatt basis. Nothing's changed. The only thing that's changed is that you're in a place where, well, perhaps labor is more expensive. I don't think that's actually the main reason. I think it's just dumb politicians and dumb regulations. But anyway, that's a separate issue. So I'm using China as an example for sort of the baseline capex, which is probably reflecting primarily actual installation cost, right? Raw materials, fabrication, and assembly and erection. Not so much regulation. Not so much stuff related to government, like environmental shit, right? Whatever. So so if you amortize that capex, and this plant, this Chinese plant is 600,000 tons per year, and it cost $650 million. And of course, this includes hydrogen gas production and purification, which is very important, right? Because all ammonia plants, when you see an ammonia plant quoted, you don't just take the price of the actual ammonia plant itself, because really all an ammonia plant is a compressor and a big converter. That's all it is. Or reactor. They call it converter. It's just a big reactor, right? So you have to obviously include the price of the steam methane reforming facility or the coal gasification facility, because I think most ammonia in China is produced from coal. I think about 80%. All right, so the capex for the first year is about $1,083 per ton per year. All right, so that's for the first year. Now, of course, we hope our plant lasts longer than 1 year. So if we amortize it, say, over 20 years, that equates to $54 per ton. And if you include maintenance, which a really conservative estimate would be about 5% annual maintenance, that adds another $54 a ton. I think that number is a bit too conservative, but ammonia plants require minimal maintenance. The primary maintenance intensive component is the compression system, but large-scale plants use centrifugal compressors, and that's what we're going to get to later. Centrifugal compressors last a very long time because you don't have any friction and you don't have any moving parts aside from the bearing. And you don't have issues of oil lubrication causing contamination of the synthesis gas. So a good estimate's about $75 per ton capex. And of course, this is less than 10% of the cost of the current anhydrous spot price. Now, what we're proposing is taking advantage of process intensification technology. So combining that with commercial off-the-shelf equipment procurement, reducing customization, so minimizing the amount of customization that we're doing, improved use of modularity, so that being able to assemble a lot of these systems in a modular fashion, and of course the most important thing, taking advantage to the fullest extent of off-site manufacturing, enabled obviously by containerization. So off-site manufacturing is obviously a much more efficient way to produce any kind of big piece of machinery, because if you think about it, when you're building an ammonia plant, you have to truck the huge reactor, most likely by road, because you're not going to be building the ammonia plant right where you manufacture the reactor. So, or I should say the converter. So the converter is this massive, 200-ton steel cylinder, effectively. And this requires an oversized load, and so you have to, it's expensive to transport that reactor from where it's being manufactured, which probably is being manufactured in Asia, and it's being transported, let's say, to North America. Then, of course, you have to erect it. When you get to the site, you have to erect it, so you need a crane, you need to rent the crane, you need to hire the operators. There's obviously safety considerations there. Weather downtime, weather-related downtime. So you have to limit your productivity due to weather-related limitations. And of course, labor costs tend to be more expensive for on-site work than in factory work, because you probably need more skill level. You have to have more customization, right? There's all sorts of reasons why producing something in a factory is a lot more efficient than producing something on site. And it's the same goes for construction, right? Modular construction is always much cheaper than site-built construction, even though you're shipping the same amount of material to the job site, right? You're shipping your wood and your windows and your steel and whatever you're making your building out of to the job site from the factory, versus from the lumber yard or from the steel mill to the site. There's the same amount of material transported. It's just that the labor is so much more productive and efficient inside a factory setting. So this simple logic applies to chemical plant manufacturing, obviously. So when you're producing ammonia from inexhaustible sources, that is water and air, distributed production obviously becomes a lot more attractive, right? You don't need natural gas, you don't need coal, you don't need to be located where that is produced. You can be located anywhere where you have a cheap source of electricity, and of course, it doesn't just have to be solar energy. I just focus on solar energy because currently that's the cheapest source of electricity. But we're going to have in the future small modular reactors, right? Because the anti-nuclear people will ultimately be defeated by the efforts to reduce carbon emissions, and so if eventually I think the nuclear industry will win out, and people will realize they're going to need significant contribution to come from nuclear, and small modular reactors will win out over these large site-built facilities for the same reason that our system works. So I could see a future where you have small modular reactors producing hydrogen from electrolytic hydrogen and using the containerized ammonia plants. So it doesn't just have to be solar. It could be wind. It could be nuclear, geothermal, any source of electricity that's about less than 2 cents per kilowatt hour. Okay, it could be higher than that, but ideally should be below that price. And of course, a lot of people say that's a tall order to meet. 2 cents per kilowatt hour is obviously very cheap. But again, right now, if you go to the UAE, I think maybe it was Dubai, they just signed a PPA, purchaser price agreement, for 1.5 cents per kilowatt hour for a big solar farm. So we know that photovoltaic technology right now can achieve those prices if you're in an environment if you're in a geography with really high irradiance. The natural gas and coal prices go up. Now they're going to go up for two reasons. They're going to go up because we're slowly exhausting these resources, but they're also going to go up because people don't want to use them because of carbon dioxide. And so yeah, you don't really want to be reliant on, if you're using a product, if you're using a chemical and that chemical is produced from a hydrocarbon, you would want to hedge against that uncertainty by substituting that raw material feedstock. So it makes a lot of sense for people to figure out how to produce ammonia from electricity, because we can always produce electricity. We can't always produce natural gas. We can't really produce it, right? We have to get it from the ground. So if it's based on solar, distributed production is only reliant on polysilicon as a commodity, and we're never going to run out of polysilicon. Silicon is about 25%, I think, of the Earth's crust. And of course, the price will continue to go down with increased production volumes. Now, regarding the price of ammonia, so if you look at the USDA statistics, which is what I use, the selling price of ammonia, the median is about 730, but there's no one selling it below 700. You look at the lowest price and look at the highest price. They don't just give you a standard deviation. They actually just give you the lowest offering price. The lowest offering price is somewhere at like 690. So no one's really offering cheap ammonia. No one's producing cheap ammonia right now. And that's because, again, the industry is highly consolidated. So you don't have any bargaining power. Of course, I explained this using Porter's 5 forces. Producers of a value-added product or chemical have more bargaining power than their customers, since the demand elasticity is quite low, meaning that you're always going to need the ammonia, right? You can't substitute the ammonia, right? So threat of substitution is really the main thing that drives. That's one of Porter's five forces. So of course the barrier to entry to produce ammonia is very high. So that again explains, that's one of Porter's five forces. It's going to be difficult to just start up, build an ammonia plant. It's hard to get capital. The lumber price situation in North America illustrates this phenomenon. That you have a small number of mills, suddenly demand increases, and the mills basically have all the bargaining power, and they charge as much as they want. Now, of course, in the end, the price does come back down, but it took a while. It took almost a year for it to come down. All right, so we can go over the situation with the solar resources. So this company called Hefei, this company in Alibaba, they're called Hefei Yangtze Solar Power Company. They offer a 1 megawatt farm. So this is a turnkey package with all the equipment ready to install for $289,000. If you were to install this module in a geography with a radiance of between 700 and 1800 kilowatt hour per kilowatt panel, you could expect 1,800,000 kilowatt hour per year, amortized over 15 years. Subtract your 0.8% per year degradation, and you get a price per kilowatt DC of 1.2 cents. Right. So 1.2 cents is very attractive. Now, of course, you have to obviously add maintenance costs. Solar panels don't really require a lot of maintenance. They just and especially if you're in a benign environment, you don't want to be somewhere where you get hailstorms or you get tornadoes. You want to be in a sort of benign environment. So you could say, oh, well, what about the fact that a lot of ammonia is consumed in places where you do get tornadoes, right? For example, the Midwest is a big farming farming belt, whatever you want to call it, and you get a lot of tornadoes. You might get hail. And so it might not be a benign environment for solar. You really want to be in the desert. And in fact, also, the Midwest doesn't really have the greatest irradiance. So, well, firstly, we're not just going to do this in North America. There's all sorts of geographies around the world where we have abundant solar resources and we might want to use ammonia. Again, I am not really saying that we are only going to produce ammonia as a fertilizer, hence needing a farm nearby. I'm also saying that it's going to be used as a fuel, because if the global governments and the global elites at Davos want to decarbonize the economy, you're going to have to find a high energy dense carbon-free fuel, and you're not going to be able to do that without ammonia. So I'm positioning myself to be on the winning side of that endeavor. Again, electrolyzer costs are going to dominate. If we're going to buy the conventional machines on the market, we're going to make our own, and we're going to use a few techniques to bring them down to about $50 a kilowatt. So yeah, that's going to be a significant contributor to the viability of this technology. Okay, so you might ask, am I the only one who's talking about this? No, I'm not. There's a guy at, I think it's Rice University, and he has this idea for the small self-contained ammonia manufacturing box, calls it AMB, and he envisions the same configuration that I do, which is sort of containerized, small-scale, distributed production model. Now, he's not using solar energy to produce it. He's using regular natural gas, which means you're going to have to build small-scale natural gas reformers. His idea is mostly, for producing fertilizer. It's not necessarily intended to be used for ammonia as a fuel. Because it wouldn't make much sense to use ammonia as a fuel if you're going to take methane or natural gas and crack it into hydrogen and then produce ammonia from that hydrogen. You might as well just compress the natural gas and use it directly as a fuel. So process intensification, automated safety systems is some of the things that he envisions in this architecture, in addition to microprocessing technology, which is basically a term for reactors, catalytic reactors, chemical reactors that make the use of very small dimensions to increase heat transfer rates. Now, for ammonia synthesis, That doesn't really work because it's a high pressure system, but for things like Fischer Trope, for ammonia decomposition, you definitely want to make use of microchannel technology. And he says here, the ammonia plant of the future is contained on one rail car, shop fabricated, and contains all the latest technology. Yeah, this makes sense. One important point that I want to make is that the number one advantage of not only the small scale system, but the fact that we can manufacture that small scale system in a factory setting is that we can use more ubiquitous components, as I said, reduce the amount of customization, and we can buy off-the-shelf components, which is going to be the number one contributor to our reduced capex. Rather than buying more specialized components, we can design our system to make use of more ubiquitous components. So that's anything from flow regulators to valves to pressure vessels to just about every component in the system. So here's an example from the Fischer Trope industry. The Fischer Trope process is not really that different from ammonia synthesis. It's an exothermic reaction. It's a lower pressure reaction, and it's a medium temperature reaction. So it definitely has some similarities with ammonia synthesis. So in this case, they find that. All right, so there's some data from the Fischer Trope industry that indicates large-scale reactors, that is over 18 feet in diameter, are actually more expensive to build per unit of volume, not just per weight, but unit of volume. Even taking into account the square cube law, that when you scale up, you find it's more difficult to build. And this makes sense, right? Because if you're going to build an ammonia converter, which is made out of pretty thick steel, you have to forge it. You don't cast it or machine it, right? That's not a manufacturing method that's used. You forge it, and forging at these large scales is obviously much more challenging. So the cost for a large reactor could be equally expensive, if not more, even adjusting for the greater volume. Okay, another huge advantage of electrolysis-based production of hydrogen is, of course, the elimination of all the impurities. You don't have sulfur, you don't have carbon monoxide, and various other impurities that are very detrimental to the longevity of the catalyst. All you have is oxygen. Now, oxygen is a quite severe poison, but the thing with oxygen is that it doesn't permanently damage the catalyst. It can be the catalyst deactivation can be reversed by just reducing it with hydrogen. So, if you do have excess oxygen, you can periodically reduce it and regenerate the catalyst. Hydrocarbon feedstocks are full of impurities, and you have to go through a lot of steps to purify them, and hence additional equipment, additional costs. So another reason why now it's easier to separate. It's not very difficult to separate oxygen from the hydrogen, and so oxygen really is not a big concern. All right, here's the crux of the matter. The crux of the matter here is that small-scale production has not taken place yet because of one principal reason. And that one principal reason is the lack of compressor technology options at small scale. So obviously, if you're building an ammonia plant, for a few hundred tons per day, the mass flow rate, in cubic meters per hour is huge. And this means that centrifugal compressors, effectively, a radial compressor like on a turbocharger or gas turbine, is a very effective compression option. Even though the pressure rise per stage is pretty low, you can just stack these stages up, and you can have a multi-stage design, and you can get decent pressure ratios. You can get up to 150 bar with centrifugal compressors, and they need very little maintenance. They're pretty cheap for their output, and they last a very, very long time. And of course, most importantly, they don't contaminate the synthesis gas with oil. That's actually the number one concern that you have. So on a small scale, and of course, I forgot to mention, they are required to operate at a full fraction of their speed. That you can't operate them at a partial load because your pressure ratio drops. The peak pressure ratio is at the highest speed, so you can't operate it at half load. You're not going to get a very high pressure ratio if you do that. So on a small scale, where you're going to be balancing your ammonia plant with that of the output of the solar farm, you're going to be shutting off the plant multiple times a day, and thus the compressors are going to have to operate at part load and be shut off and on frequently. This effectively means that you can't use diaphragm compressors because diaphragm compressors are not able to tolerate frequent shut off and startup because the diaphragms become damaged. So according to, so from what I've found, a diaphragm compressor operating with frequent startup and shutdown can last as little as 6 months before replacement of the diaphragms required. Now, of course, diaphragm compressors are the reason I'm talking about diaphragm compressors is because they're the only reciprocating compressor technology that that can enable contamination-free syngas compression, because you don't have any oil in contact with the gas. The diaphragm is what separates you're compressing oil. The oil pushes the diaphragm up, and the diaphragm is what actually compresses the hydrogen. They're usually used for compressing either corrosive gases that you don't really want in contact with the piston, or they're used to compress gases that you want to keep really clean and free of oil. Now, you can use conventional piston compressors with oil lubrication, but you're going to have to figure out a way to do downstream purification or use absorbents or some kind of a filtration system to remove the oil. So if one could figure out an effective way to do that, you might be able to just use regular reciprocating compressors. I haven't really found any good absorbent material that could be used to absorb these trace impurities of oil. What I'm looking at doing is using ionic liquid compression, and ionic liquid compression does sound kind of exotic. It was first used by Linde for hydrogen compression, hydrogen fueling stations. And what's nice about the ionic liquid compressor is it can operate in an isothermal. It can operate basically isothermally, and that means that the theoretical efficiency of an ionic liquid compressor is substantially higher than that of conventional mechanical compression. Now, ionic compressors are effectively a compressor where you pump an ionic liquid, and ionic liquids have very interesting properties. They are not miscible with the hydrogen or any gas for that matter. They have no vapor pressure, so you don't really get any mixing of the gas with the ionic liquid. They also have good tribological properties, so they can serve as lubricants. And so what Linde basically did is that they used hydraulic fluid, and the hydraulic fluid would push up a piston, and then that piston would push the ionic liquid, and then the ionic liquid would effectively serve as a compressor, or as a piston, I should say. So you don't really want to pump the ionic liquid directly. Rather, you have a piston that pushes the ionic liquid, and then the ionic liquid actually is what compresses the hydrogen. Has found that this particular compressor technology is about 10 times more compact than the conventional reciprocating compressor. That's important because what we're doing is trying to downscale and process intensify. We want to make all of these components as compact as possible so that we can fit them inside of our container. Okay, so as I mentioned, the ionic liquid has properties of a lubricant, so you don't need any oil. The ionic liquid is not miscible. It's not going to contaminate the gas, and it's isothermal. So you can reach close to 100% compression efficiency. Even more importantly, the ionic liquid compressor is more reliable, and they claim about a factor of 10 over that of conventional mechanical compressors. And you only have about 8 moving parts versus about 500 moving parts in the conventional compressor. Okay, they've been around since 2001, so a lot of the original Linde patents have expired. So companies that want to build these are free to do so. There's some companies in China that are investing in using or developing ionic liquid compressors. I think there's a Linde compressor right now that's being used in China for hydrogen filling stations. Again, my understanding is that ionic liquid compressors are almost exclusively used for hydrogen fueling stations, and for that reason, they can operate up to 900 bar. So misspoke when I said it was 10 times more compact. It's actually 25 times more compact than a standard reciprocating compressor. So, for example, a 900 bar, 370 cubic meter per hour ionic liquid compressor has a height of 1.1 meters, while a 100 cubic meter per hour, 440 bar reciprocating compressor has a height of 3.5 meters. Adjusting for the pressure and mass flow difference, the improvement is nearly 30 times. So as for what ionic liquid you want to use, it looks like the ionic liquid is going to be an imidazolium-based ionic liquid. So, and there are many different ionic liquids available to choose from. You want to find one that has good tribological properties and is not miscible with a hydrogen, and ideally is not corrosive to the material. So it was found that the imidazolium trisulfate ionic liquid was not corrosive to stainless steel 316. So that is more reason to believe that the longevity and reliability of an ionic liquid compressor would be satisfactory and or definitely exceed that of a conventional oil lubricated and or diaphragm system. Okay, here's an interesting fact. So compression energy expenditure is logarithmic. So you only need 1.2 times more power to compress hydrogen to 900 to 1,000 bar versus 200 bar. So effectively, as you get to higher pressures, the energy required to compress is reduced. So this actually is very interesting. That, of course, is a good thing for the guys trying to do high pressure, fuel cell vehicles. But it's also interesting for us because if we want to process intensify the ammonia plant, the number one thing we can do is increase the pressure in the reactor. And when you increase the pressure, the output, let's say if you take kilograms of NH3 per kilogram catalyst, or the turnover frequency, mole NH3 per gram catalyst, that's the activity of the catalyst, will increase dramatically at higher pressures. There's one caveat though, at higher pressure the catalyst is more likely to deactivate because any impurity is going to penetrate the catalyst much more rapidly.